and how tough the material is, resistance to crack propagation. So it's very similar in this case, resistance to crack propagation in this case. And in fact, we did a finite element analysis on these materials. The red curves here showing graded structures. Here is 1 millimeter thick, and this one 0.4 millimeter thick, versus ungraded, which is blue curves, 0.4 millimeter and 1 millimeter. What this one shows us is the tensile stress in the material when the plates and the flexure and the bottom surface, the lower surface of the material. In ungraded materials, we know that if you load a zirconia bar or zirconia plate in tension, what we experience? The absolute lower surface has the highest tensile stress. Is that right? 3-point bending, we know that. Fracture is going to initiate at the tensile surface. That's exactly what finite element is pointed out to. And on the surface, you have about stress about 1 gigapascal. That's just to reflect the strength of the zirconia, somewhere around 1 gigapascal. And as you're moving away from the surface, come up to the neutral axis, the stress reduces. By the time you reach neutral axis, somewhere here, 0.5 millimeter thicker, because the whole plate is 1 millimeter, the stress, the tensile stress should be diminishing down to 0, and then above that is compressive stress, right? Interestingly, in the graded structures, the surface stress now very similar to ungraded materials, also about 1 gigapascal. But what happens is now it pushes the maximum stress into the interior of the material. Some people will tell me, what is this good about? Because you still have a lot of stress, and just pushing to the inside, it's not on the surface. So, but we all know that ceramic fracture most of the time is due to the surface flaws and damage from handling, from other things, right? So if you are able to move the maximum stress away from the surface, you will greatly improve the fracture resistance of the ceramics, because internally you don't have a lot of handling defects on the surface. It's mainly material intrinsic defects. So you probably just move the maximum stress away from the surface, which will more likely generate a fracture. And we also went ahead this composite beam theory. I'm not going to bore you on this thing. And we wrote this stress distribution in the materials and solved these equations. But what I'm going to show you is the results are very similar to finite element analysis. Now, here I have a beam, a graded zirconia beam, about 1.2 millimeter thick. All right, from here to there is 1.2 millimeter thick. And we load it in the middle center with the indenter here, giving a load about 800 Newton there, and loaded. So our experience will tell us for ungraded, if the material is not graded, you're going to have a linear distribution of the stress. The bottom surface, you have the highest tensile stress, and it gradually reduce when you reach the neutral axis, and then this part is a compressive stress, right? But if you tailor the surface elastic modulus, what you can do is now you can reduce the surface stress from 1100 down to 400 megapascal. You can push the maximum stress into the interior of the material. So that makes the material more resistant to fracture. And in fact, we went even one step further. We worked out the thicknesses ratio, the total plate thickness to the graded layer thicknesses, and on the effectiveness of the stress reduction. And we found out that most effective region, interestingly, is in the range of 0.4 to 1.5 millimeters. That's coincidentally this is the thickness of our dental restorative materials, right? So in fact, if you make graded restorations, and probably is the most beneficial area, region for this kind of surface treatment. And I'm now going to move on to the last topic I'm going to cover, is the sliding damage resistance. Remember, I spent so much time sliding on a surface. It's so easy to initiate the crack and much aggressive to propagate the crack. Now, if you slide on a surface, this is the piece of porcelain now, 120 Newton, massive cracks on the surface form. All right, we call those cracks. You see those cracks, like herringbone cracks, like those herringbone fish scales. And in fact, if you cut across or look on the side, I haven't shown you the I should really show you a picture. It is what we so-called distorted cone cracks, the partial cone cracks, the little tails there. Now, in the case of porcelain, 120 Newton killed. Even 80 Newton, the crack formed. All right. In my lab, you use tungsten carbide indenter, slide across, 50 Newton crack form. But people may say, oh, you use tungsten carbide. What about glass? Porcelain you use. What we found out is the elastic modulus, the hardness of the indenter, will have effect on the materials, but the governing factor, in fact, is the friction coefficient. If the surface is rough, even you have a soft indenter like a glass and porcelain sliding on the surface, crack will form. So that's probably the message that tells us you got to do your best to make sure the surface is smooth. In the case of zirconia, it takes about 1,000 Newton to generate those herringbone cracks. And in case of graded structures, 2,000 Newton, you only see sort of initiation of some cracks on the surface. That's what we did with one sliding cycles. And now we also show you, if you do cyclic fatigue test with this aesthetic surface glass layer on it, 20 micron thick, and you conduct the cyclic fatigue test with graded structures, what we did was 200 Newton, 2 milling cycles sliding on a surface. And this is the top view, what we see, the contact area with a little nose in the front. And the side view we see is very smooth crater here. And you compare to zirconia, very similar. If you zoom in, what we see is the contact area from the residual glass to the graded structure to the monolithic zirconia core is a smooth transition. There's no cracks there. So there wouldn't be any potential chipping or anything formed. And in the case of zirconia now, what we see is in the front of the contact, in fact, you do have some rough surface and a crack already formed. If you do porcelain veneer zirconia, 200 Newton only lasts about 50,000 cycles. All those cracks propagate down to porcelain zirconia interface. I'm going to wrap it up real quick now. First, I'm going to show you that with graded structures now, we are able to sort of tailor the shades. You can have sort of white color shades and the yellow shades, and we can also do somewhere between them. And that's compared to monolithic, so-called single layer zirconia. We definitely have the advantage of providing some shade, shaded variations in there. And this is the single crowns, full coverage single crowns with graded yellow shades, graded white shades compared to a monolithic zirconia and compared to porcelain veneer zirconia. So we are able to match the shades with these materials. The last thing I'm going to talk about is perhaps it's more to Thomas and Jason and Bob, because we know that you CAD-scan the material, now you have anatomically correct the shape. By the time you infiltrate glass into it, would you cause two problems? One is phase transformation of the zirconia, and two is would you introduce residual stresses into the material? And so what we do is we did one of those crowns. In fact, it was one of those yellow crowns. I go back. We cut across this way, and now you see the cusp cup. It's about 2 millimeter thick here, but the rest area can be varied between 1.1 to 1.5 millimeter. So let's call average about 1.5 millimeter. We infiltrate both top and bottom. What we see is we section it, we see residual glass on the surface, and followed by graded structures. The interior is zirconia. So what we do now, we do X-rays, micro X-ray diffractions. The beam size is about 10 micron. We map from the surface in 50 micron step going in there to do two things. One is to detect if we have monoclinic zirconia phase in this system. Two is to detect if we have any residual stresses in it. That's more complex analysis, but X-ray is able to do this. So what we did is we showed that from surface in the glass, you see pretty much amorphous. There's no peaks there. That's a 2D detector here. And by the time you get into graded structure, you start to see some crystalline peaks. And then you go deeper, the peaks getting darker, and then you go to the interior now, very distinct, the zirconia peaks come up. And if we compare to the powder X-ray diffraction files, and those peaks, indeed, they are tetragonal zirconia peaks. There is no monoclinic phases there. And finally, that we can etch the integral surface, and then now you have a glass mixture glass zirconia surface, but it's a three-dimensional rough structures. We can salinize it and the cement, and also we can, without etching it, we can put alumina on it. We can facilitate cementation. And finally, just a conclusion slide, and to show you that by grading the surface, proper design the surface, we are able to improve the sliding contact damage resistance, flexural damage resistance, and also now provide the options for shades, resin bonding, as well as now we're going to test here is the hydrothermal degradation resistance. And finally, I would like to thank my postdoc, Dr. Ren. She just started in my lab this March. And my previous postdoc, I'm pretty sure you all read his paper, Dr. Kim, Jae-won Kim. Now he joined a biomedical company in Long Island. So I'm very proud of him. And my mentor here, oh, that's too fast. I was going to show you that. Now, I blow the whistle. Anyway, okay. Now, my mentor, Dr. Long, my collaborator, Herzl Hai from Tel Aviv, and also head of department, Ben Thompson. Everybody knows Ben Thompson and Diane Rico. And Lenny Murata is a dental, he has a dental lab. And thanks the NIH, NSF for the financial support. Now, the reason I'm showing you this photo here is this one was taken Saturday by one of your colleagues here. And what thing amazes me is this city really make me feel young. I hope I can keep it that way. Thank you very much.